Good morning, Ben Cohen. Hope you're doing well. Back to our calculus class. So we've gone over the idea behind the limit and how that applied to definition of a derivative, and we use that to kind of explain the power rule and product rule so far. So the idea is blue. For power rule, if you have something where you have f of x and that equals x to the n, then f prime of x, the derivative of f of x, would be something along the lines of x to the n minus 1. Whoop. And then we had the product rule, which was if you have something that's along the lines of f of x equals u times v, which was, each of those were themselves a function of x. So you had u of x, v of x, and you wanted to take the derivative of all this, f prime of x, you would get something that was uv prime plus u prime v. And that's the idea of how you do the product rule. Well, today we're going to talk about constants, pretty straightforward really. And then sine of x, which is kind of the gateway to the rest of the trigonometric equations. And then the big one, which is the chain rule. And after that, that's pretty much everything you need to know for derivatives. There's a lot of ways of applying it and using them, but as a foundation, that's pretty much the bricks you use to build your pyramid. That is the king penguins that live on your iceberg, so to speak. So we're going to start with a constant. So you have something along the lines of, change color, purple, f of x equals c. For c is for constant, but in this case I'm just going to say that f of x equals 3. One constant's pretty much as good as another, and I like things that are a little bit more concrete. And my justification for the derivative of constant is going to be pretty informal. So the derivative of a constant is 0. So the way to see that, or the way I like to see that, is let's say this is 3, so that'd be 1, 2, this would be the x-axis, this would be the y-axis, maybe that'd be the y-axis. Yeah, I call that the y-axis. This is the f of x equals 3, well the derivative is just the slope. And we look back at the definition of the derivative, we have f of f prime of x equals, slide over slightly, f of x plus h minus f of x all over x plus h minus x. So when we plug in f of x equals 3, we get 3 minus 3 all over h, which goes to, and this is all limit as h approaches 0, and the limit's still down here too. So then we get 0 over 0, which is an indeterminate form, and it kind of gives us a little bit of a difficulties, challenges. It's an adversity that we don't want to tangle with. So for me, the easiest way is, all right, we have a straight line. The slope of that straight line is 0 because slope is defined as rise over run, dy dx. And so if you say instead of limit as h goes to 0, h equals, I don't know, 4, which is, the bigger h is, the worse the approximation is. But if you have a bad approximation that gives you 0, you can kind of feel that, okay, this is probably where this is going. And it stays at 0. So you probably don't need any more convincing. Like, okay, I see. That line is straight, completely horizontal, slope is 0, derivative is 0, not that difficult. True. It's not. But I always feel bad when I don't have a good solid reason. Like, oh, this is the obvious reason why. So the derivative of a constant is 0. Now, on a tangential note, not actually related to trigonometric functions, just slightly related at a singular point, if we have the function f of x equals a constant, again we'll say 3 times something that involves a function of x, we can then just keep the constant there. It doesn't have to go to 0. Whoop, whoop. And then take the derivative of the second portion. So this would be 3 times 2x equals 6x. And similarly, if you had f of x equals 9x cubed, f prime of x would then equal 27x squared. And the idea is you just keep the constant out there. And you might be like, wow, that's kind of strange. It kind of sort of is. And the justification for why that exists in life is the product rule. And so if you look at this, the product rule, going through this quickly, uv prime equals uv prime plus u prime b. Where you can say here, all right, u equals 3, whoop, v equals x squared, right over there. U prime equals 0, v prime equals 2x. And so what you're left with then, when you actually solve it, u 3 times v prime, which is 2x, plus u prime, which is 0, times v, which is x squared, and that gives you 6x. Same as we said above. And so my kind of haphazard, well, you just kind of leave the constant there, you don't worry about it, you factor it out, then you put it back in, that actually pretty much sort of works. And for me, it's easier to visualize that, all right, just don't worry about the constant, take the derivative of the x, then put the constant back on. That sort of methodology of doing it that way, of kind of feeling like you factor it out, though it's not really technically accurate, what you're doing is the product rule here, it works well. And when you're going through a bunch of problems and you're doing them quickly, and it's a time-sensitive issue, you don't want to think product rule when you see 3x squared. You want to think of, okay, we take the 3, we take the derivative of that, and we have 6x. And that's all the mental gymnastics you want to do. Bam, done. Put that on the iceberg, leave it alone. So that's how I deal with constants. I know they're not particularly hard, but it's worth having a little bit of formality to be like, okay, this is how it's done. So the derivative of a constant is 0 because the slope of the graph is horizontal. And when you multiply by a constant, and you have a constant as like a coefficient, you can think and feel like you factor it out and then put it back on when you're done. But in reality, product rule is happening under the hood. Okay, so that is the idea for constants. Now we take on the challenge of, okay, what about sine of x? Let's see, I'll leave these guys up there because they're still important in life. I'll add on though, whoop, f of x, I'll rewrite these. I can do a better job. Whoop, whoop. So if we have, zoom in slightly, a little bit to the left, our power rule, f of x equals x to the n, that will imply that f prime of x equals nx to the n minus 1. And if we have f of x equals u times v, which u and v are both functions of x, then f prime of x would be, I'm going to need a little bit more, there we go, uv prime plus u prime v. So then we have f of x equals a constant implies that derivative of f of x equals 0. Okay, so now on to sine of x. Let's say, change colors. I always kind of spend a lot of time in this corner here. Ooh, yeah, no, I like that corner. It's a good corner. F of x equals sine of x. Okay, so first thing we do is like, okay, we don't know how to do this, so we're going to go by the definition of a derivative. So our definition of the derivative is f of x prime equals limit as h approaches 0 of, let's see, what is it? F of x plus h? I think it's f of x plus h minus f of x all over x plus h minus x. Excellent. Excellent. You get it? Never mind. That's terrible. Okay, so if we look at this from a graph, we have some graph, looks kind of like this. And what we're doing is we're like, all right, we take this point, we're like, this point is x, this point is x plus h. We take this distance here, like this, and there we go. We have f of x here and f of x plus h up here. And that's how we find the derivative with respect to x of f of x, a function of x. But there, we talked about a little bit earlier, there's no real reason why we have to do it with x and x plus h. As long as when we take the limit as h approaches 0 and it encompasses, collapses on, approaches x, we're fine. Like, when you look at this, you might think, well, wait a sec, that's going to skew our answer off to the right of what x is, because it's going to be off that way. Wouldn't it be better if we took, a point here, x minus h, and then this would be f of x minus h, and did that instead, because it's all the idea of rise over run, dy dx. And that's true. It wouldn't be better because they're both limited as h approaches 0, so they're both infinitely good approximations. And even a mediocre infinitely good approximation is just as good as a really good infinitely good approximation. Once you get towards infinites, they all kind of blur together as adequate. And so we could do x minus h and x plus h, but it's usually just easier to do it like this. Well, this time it's not. So for f of x equals sine of x, I think one of the easier ways to see this derivation or where it comes from is to use with f of x plus h minus f of x minus h. So I'm going to rewrite our derivative here. Do I have room? I don't think I have room. I'm going to move this over slightly. Whoop. Make sure I still have purple, because I like purple. Equals, let's see here. I'll do f of x plus h minus f of x minus h all over x plus h minus x minus h. There we go. Yep. We're going to say then that this will also equal, plugging in sine of x plus h, whoop, like so, like such, all over, and then I'm just going to write this as 2h, because you get plus, minus, plus. Okay, and so we're left with this, and this is all limit as h approaches 0. I just didn't write it in because it's easier not to. And we're like, oh, okay. There are 3 trigonometric identities that I memorized in life. I guess 4 if you count the Pythagorean theorem. But they go like this. And this is just straight memorization. Penguins on the iceberg type thing. So we have cosine alpha, cosine beta, 2 equals, scooch over, cosine alpha minus beta plus cosine alpha plus beta. And this is the first one. And this is just, I just straight memorize it. These are used a lot for double angle formulas. And when you're like, well, how do you find the integral of sine squared of x? I know you guys don't even really know what integrals are yet. Trust me, you will at some point. These are useful. So then we have this, and then it's like, well, okay, what if instead of cosine, we change the sign? So sine of alpha, sine of beta. Well, all we do then is we do the same thing as above, but we change the sign. We go from positive to negative. So, yeah, okay, that kind of sort of almost makes sense in a weird mnemonic sort of way. Not actual logical, but mnemonic. And I'll stick with green. What if we have one sine and one cosine? Sine of alpha cosine of beta, and specifically in this case, sine of alpha is first. So then we go to sine of alpha minus beta, plus, we go back to our original function here, and we just change our original from cosines to sines. Sine of alpha plus beta, okay? And then don't forget the 2 over here. And these almost are what we want. So there's kind of sort of an extra one, fourth one, fifth one, I'm not sure. And you will almost never use this. But I'm going to show it to you in this time. So you basically say that alpha equals beta, and you say that beta equals negative alpha. And so when you plug this in, what happens is you get 2 sine of beta cosine of negative alpha equals sine of beta minus, minus alpha. Put an A there. Should have made, does it matter? It doesn't matter. Okay. Whoop, whoop. Extra parentheses. That is important though. Plus sine of beta minus alpha. You might be like, wow, that's kind of a strange way. How did you think of that? I didn't think of it. There's a lot of smarter people than me out there in life. One of them thought of it. Okay. Now we're going to simplify things a little bit. I'll stick with purple. And so I'm going to move cosine over, and this is cosine of alpha. Cosine of negative alpha is the same as cosine of positive alpha. Cosine is an even function, so it basically means that cosine of negative x equals cosine of x. Cosine of 2 is the same as cosine of negative 2. And sine is an odd function, meaning that sine of negative x equals negative sine of x. Basically, the negative can carry outside. It's just something you learn in life, worth knowing. Sine beta equals, and then here I'm going to do sine of alpha plus beta, because the double negative makes it positive. I'm going to do minus sine of alpha minus beta. Because what I did here is I took out a negative and basically switched the order of the alpha and the beta. So this is our last equation here. And what we do then is we look at this, and I'm going to take this, try and copy it. Can I do that? Get everything? Get a little dot in the sign. That's probably close enough. Oh, wow. Okay. Kind of fit it in right there? Okay. So the idea that we're going for here is green. No, blue. Definitely blue. Okay. So we're going to say that with our new equation, alpha equals x and beta equals h. So you see here, alpha x, beta h, we can kind of just plug things in. And so what we get then is this equation up here is equal to 2 cosine of, alpha is x, sine of h all over 2h. And h's cancel, and we're doing limit as h approaches 0. So the question then is limit as h approaches 0 of cosine of x sine of h over h. And so the question becomes, what is the sine of h over h? And you'll see this probably in most calculus courses where you're trying to find out the limit as h approaches 0 sine of x over x. It's kind of a foundational, popular question. And if you look at a graph, it becomes pretty intuitively obvious. Yeah, red, ooh, orange. You have sine of x looks something kind of like this. And then you have cosine of x, which looks something like, I should have picked something with more contrast, like that. So it kind of makes sense looking at this that you're like, okay, sine of x right here, that slope kind of looks like 1. So it's probably going to be 1. It is 1. The more traditional way of how you prove this is use something called L'Hopital's rule. And L'Hopital's rule basically means you take the derivative of the top, derivative of the bottom, and then you take the limit again and see where it gets you. But for us, that'd be kind of circular reasoning because we're trying to do this to find out what the derivative of sine of x is. And so if we take the derivative of sine of x to find the derivative of sine of x, it's kind of it could catch-22, if you will. So it kind of feels kind of cheating to use L'Hopital's rule to prove it. There's actually another really good proof out there that uses the squeeze theorem. Basically, it says something along the lines of cosine squared of x is less than or equal to sine of x over x, which is less than or equal to 1. And what it shows then is for the limit as x approaches 0, this goes to 1. 1, well, it's already at 1. And so if you have something that's between 1 and 1, well, then that's probably going to be 1. And that's the idea behind the squeeze theorem in general. And so then that shows that, okay, that's going to be 1. And so what we get then is this becomes 1, and we have cosine of x. So f of x equals sine of x. F prime of x then would be cosine of x. And this is actually kind of a big deal. And this should be, a permanent resident on your iceberg. This is just instill it in your memory, burn it in there. Grab a piece of paper, write it out a few dozen times until it drives you slightly insane. It is good to have this as a bedrock of your memories, of your long-term memory, that this is the derivative of sine of x is positive cosine of x. Specifically, they have the same sign. The mnemonic that I use to know that, or feel that, so to speak, is if you look at this slope right here, the slope of sine of x is 1, which is positive. And if you think of the graph of cosine of x, which looks like this, then cosine of x starts off positive. So if you look at the 0, the derivative of sine of x at 0, you're like, okay, that's a positive number about 1. And you think of cosine of x at 0 would be 1. So from a graph point of view, you're like, okay, that slope kind of equals that graph. This slope of sine of x kind of equals the value of cosine of x at 0. And if you can remember that one single point, then you can kind of help you remember that, okay, fx equals sine of x, f prime of x then equals cosine of x, specifically positive. So that is something good to remember. And the reason why it's good to remember is, purple, dark purple. On a slight tangential note, if f of x equals cosine of x, then you get f prime of x equals negative sine of x. And so for cosine, you have the same relation as you do with sine, except that you get the opposite sign, which is why it's important to memorize this right here, so that when you do the derivative of cosine of x, you can be like, okay, it's similar, but just the opposite. So this is the one I memorize. This is the one that I kind of do. And like, okay, same thing, just opposite sign. Okay, so that is the idea behind sine of x. Ooh, that looks like a lot more than I intended to write. Meh, such is life. Sine of x. Okay, so now that we have that, erase this, kapow. So satisfying watching everything kind of just go away. Breaks my heart slightly. Okay, back to blue, write up our new rule. Well, it's not new, but it is new to us, so that kind of counts, I guess. Sine of x, f prime of x equals cosine of x. And these are all things that you should have memorized for the AP exam. This is a small subset of the things you should have memorized. Okay, so now we're going to look at the chain rule. And the idea behind the chain rule is nested functions. So people are coming from a programming point of view, like, oh, okay, nested functions, I understand that. And you kind of have an understanding of how careful you should be with nested functions. How you can change something small and it just spirals out of control after all it's nesting. That's kind of sort of the same caution you should have with derivatives and such. So I'm not gonna derive it. You could totally derive it. You do the same idea of, all right, definition of a derivative, plug in a nested function, and you go from there. And totally possible, but I don't believe it adds a whole lot of value looking at that specific derivation. Some proofs and derivations are useful because they help you understand things better. Some of them are not. So if you have the function f of g of x, and you can see my notation kind of changes here. It does. And so for f, when I do the chain rule, I usually use f of x and g of x. But when I do the product rule, I use u and v. There's no real legitimate reason why I do that. It's just that it feels that things kind of flow smoother that way. With f and g of x, it's easier to put the little parentheses for, like, okay, as a function of x. Where u and v, it kind of feels more natural for them to stand alone as u and v, where the of x is just implied. I like to have the of x when I'm doing the chain rule, because then it's very explicit, very obvious, unambiguous. So like, okay, these are a function of x. Okay, so f of g of x is going to be f prime of g of x times g prime of x. So you kind of like you're multiplying by the derivative of the interior function. So I'm going to, instead of giving you a proof, so to speak, I'm going to tell you an overly cumbersome story, which will kind of insinuate the importance and kind of give you a feel of the implications of the chain rule. So you're there in the woods, and there is some sort of wolf. Is that an ear? Is that an eye? I'm not sure. I'll draw it like this. Ear, eye. That seems reasonable. And you want to run away from the wolf. And the wolf, it runs at a speed of, I'm going to say, distance covered of wolf will be t squared. And so if we draw up a little table of his speeds here, we'll say, like, all right, we'll say his time will be here. This will be distance wolf. We'll say 1, 2, 3, 4, 5. 4, 5. And 6, 7, 8. There we go. Oop, change colors. It's probably an easier way. No. Probably an easier way for me to do it. So at 1 second, he'll be at 1 meter. At 2 seconds, he'll be at 4. 3 seconds, he'll be at 9, 16, 25, 36, 49, 64. Did not need that many. And you're running from the wolf. And your concern is not so much to be your distance away from him, distance person, distance you. You're not like, well, I want to be 10 meters away from him or 2 meters or whatnot. Your concern is more with time. And so the idea is being 10 meters away from him, that's like 3 seconds when you start. But like if you look up here at like 6 and 7 seconds, that's less than a second. So the idea is you don't care about the distance you're away from him. You want to be time away from him. And like you specifically want to be 2 times the time away from him. I'll draw an arrow here because this is not the full equation yet. And so the idea is you want to be twice the time away from it. So let's see here. Do 1, 2, 3, 4, 5, 6. And do distance person. And I'll change colors just to either clarify or add confusion. And so the idea here is at 1 second, you want to be where the wolf would be at 2 seconds. So 4. And at 2 seconds, you want to be where the wolf would be at 4 seconds. So it'll be 16. Let's say 36. 8 would be 49. And 5 would be, I don't know, would be at 10 seconds, which would be 10 squared, which would be 100. And I'm going to leave off 6 because I grow weary. And so the idea here then is these will be our distances we are. So the question would then be, how fast are we moving the person? How fast is the person moving at t equals 4 seconds? So right here. Well, you'd be like, the way you find speed is change in distance over time. So our change in distance here, if we approximated this, we'd be like, all right, so this is the point that we're looking at, which is 4. We do 100 minus 36, because that'd be our distance, over 5 minus 3. I know people don't actually run with this kind of crazy acceleration forever. We're going with this. So 100 minus 36 is 64, 5 minus 3 is 2, and we're left with 32 meters per second. Ah, okay, that seems reasonable. And the way we did that was basically made up the graph and picked out the numbers. And this is just an approximation. But how would we do that from a more mathematical, formal sort of way? Well, our distance here, we could write this distance person, the equation here, is basically plugging in this 2t into this above equation for t. So in effect, our distance would be 2t squared. And so what we have here then is a situation where we're not really looking at the distances, we're looking at a common variable common to both of the distances, specifically t here. So if this is the distance and we want to find our speed, we take the derivative of distance with respect to time. The speed, or velocity, or speed, to find that, you take the derivative of the distance with respect to time. Or, if that feels funny, delta x over delta t. Again, the derivative is just a delta something over a delta something else, which you're taking the derivative with respect to. So I am going to rewrite this in terms of x, just so it looks more comfortable for us. So I'd say f of x equals 2x quantity squared. So this, for us, we really don't know how to evaluate this with the tools that we have, because we kind of have a function, 2x, inside another function, exponential 2. So we're like, all right, this is a power function, but this is also the constant. So the way we would do this is we would rewrite this as f of g of x equals 2x squared. Yep. I don't know why I'd erase things like that. There we go. Boom. Gone. And so in this case, f of x would equal x squared. G of x, the interior equation or function, would be 2x. F prime of x would be, this is just the power rule, so we can do this, and g prime of x would equal 2. And we know from the equation that I just stated earlier without proof or real justification, the chain rule is f of prime of g of x times g prime of x. And so from here then we can be like, okay, so f prime is 2x times g of x for x would be 2x. So here, whoop, whoop, this plugged into there, times g prime of x times this one times 2, and we're left with 8x. So the distance of the person is 2t, quantity 2t squared, but I'm going to say the speed of the person, which is the derivative of distance with respect to time, is 8x. And if we look at that, therefore, the speed of the person at 4 seconds would be 8 times 4, so speed person at 4 equals 8 times 4, which is 32, which would be 32 meters per second, which is the same as our approximation. Most approximations don't work out that well. But this case is kind of like, okay, 32 is pretty close to 32. Bam. Probably true. And so that's the idea behind the chain rule. Now, back up a little bit. You probably looked at this equation and thought, wait a sec. Why did we make that complicated? I'm just going to take this and rewrite this as 2x times 2x and use the product rule. No, you're going to make it even simpler. You're going to say, all right, I can not FOIL per se, but multiply these out. So you have 4x squared. Then you take the derivative, so f of x equals 4x squared. Therefore, we'll do our power rule and constant, which is 8x. Bam, done. Yes, in reality, if you're presented this problem, you should not really do it with the chain rule like we said. You should simplify it out, expand it out, and then just do the power rule. Much, much easier. Much, much simpler. But it is kind of reassuring to be like, okay, we did this problem in two completely different ways and yet got the same answer. So we'll go through a few more examples with time of the chain rule. The idea of the chain rule is it helps you with nested functions. We'll specifically go through it next time when we talk about the tangent of x, and the quotient rule. A little foreshadowing, I don't actually believe the quotient rule exists. So the chain rule is useful for nested functions when you have a function inside of a function. And a quick little, not caveat, but addendum. I like addendum. Postlog? Prologue? I should look up more of those literary terms. Okay, so f of g of x can be written as, and you'll see this notation sometimes, f circle g. Same thing, exact same thing. You'll also sometimes see something like dz dx, where you have a function of z, and you're taking the derivative function with respect to x, and this would be the same as dz dy, the derivative of z with respect to y, times derivative of y with respect to x. And this is the same as, you have z as a function of y, where y is a function of x. Therefore, it seems reasonable that the derivative of this would be z prime of y, which is what this is right here, times y prime of x. This is very similar to this same idea we had up here. So these are just different ways of writing the chain rule, and if you're not really familiar with these sort of notations, it can kind of catch you by surprise. So especially in physics, you'll see this sort of notation quite a bit. And it's good to be able to look at it, and for me, I always try and go back to this sort of nested with parentheses notation, the sort of thing you'd expect like on an Excel spreadsheet, because I feel much more comfortable with that. It feels more obvious, it feels less ambiguous, and it just feels easier for me. One of the popular parts of this is this notation is kind of easy to remember, because you're like, oh, cancel. You really can't do that. That's not the way it works. But as a mnemonic, that kind of helps you remember the chain rule. I like to remember this. You have the chain rule of f of g of x derivative equals f prime g of x times g prime of x. I don't like any no fancy mnemonics, just bam, memorize. I know, I have the memory of a goldfish. I try and avoid memorization whenever possible, but this is one of those times in life where you're better off just hunkering down, memorizing it, and moving on with life. So that is the idea behind the chain rule. if you feel uncomfortable with it, which you probably do if you haven't done it about a billion times, fear not. We will run into the chain rule about a gazillion times along this. It's just part of life. Okay, so now we're going to go through an example. So let's say here we have light blue, definitely light blue. We have x to the fourth. F of x equals x to the fourth. So first thing, we're going to look at this as x squared squared. And so we're like, okay, this is a chain rule problem right here. So this is going to be f of x equals x squared. G of x also equals x squared. F prime of x equals 2x. And g prime of x equals 2x. And therefore, when we put it all together, we have f of g of x derivative equals f prime of g of x times g prime of x. We get f prime g of x is 2 times g of x, which is x squared, times g prime of x, which is 2x. We're left with 4x cubed. Okay, so that's how we solved x to the fourth. So now we're going to do this using the power rule. So we could say that, all right, we have x to the fourth. We have our power rule, where for power rule, we have n x to the n minus 1. This will be the derivative. This will be the f of x. And so we have f prime of x equals 4x cubed. Nope, that's a terrible 3. Terrible 3. Bam. Excellent. 4x cubed, 4x. Same answer. Seems reasonable. Okay? So let's look at this one other way then. So we could say that, all right, we could take our x squared squared, and that just is f of x equals x squared times x squared. We could also do x to the first times x cubed, but we're going to the squared thing, so let's keep going. We could say u equals x squared, v equals x squared. I should probably write up here the uv prime equals uv prime plus u prime v. U prime equals 2x, v prime equals 2x, and we are left with f prime of x equals, wait a second, let's actually take a look at this, x squared times 2x plus 2x times x squared, which gives us 2x cubed plus 2x cubed, which gives us 4x cubed. Okay, so the idea here is we took three different rules here, and we were able to solve the exact same problem in 3 different ways. In the thought process, we're like, well, okay, which way is best? It depends on the problem. For this one, definitely the power rule. That was so much easier. Just like, oh, boom, 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 done. If you can do the power rule, you're probably better off doing the power rule. Most problems that you come across won't have this amount of flexibility. And even then, like I said, the power rule is by far the best option for this solution. And so there really isn't that much choice in which one to do. But it's a good exercise to be like, all right, we have this x to the fourth. We can look at it as the chain rule. We can look at it as a product rule, or we can look at it as the power rule. And it's all different ways of using the tools we have, and it kind of gives you a sense of, okay, maybe this math stuff isn't just hojo bojo, isn't magic, and it actually works and has some consistency, and it gives you confidence in the tools that you use. So that is the idea behind the chain rule and kind of how it ties into the hierarchy of all the other derivative rules that we've come across so far. Derivative rules that we have, which are just subsets or special ways of using the definition of a derivative, the f of x plus h minus f of x all over x plus h minus x, limit as h approaches 0. And so that's the idea behind that. Fundamentally, these are all the tools you're going to need for derivatives. Next time we're going to go over tangent of x and the quotient rule, and then we'll probably also talk a little bit about implicit differentiation and give a bigger view of the wider world of calculus. So thank you much. I appreciate you stopping by, and I will see you next time. Thank you much.